In the heart of Beijing, the final moments of a 13.1-mile race recently offered a glimpse into a shifting mechanical limit. Living, breathing humans crossed the finish line red-faced and covered in sweat, ready to collapse into a familiar heap on the ground. But standing right next to them, completely unscathed and without a single bead of sweat, were machines. This specific humanoid, named Lightning, covered the 13.1-mile distance in a recorded 50 minutes and 20 seconds. To understand that speed, look at the human world record holder, Uganda's Jacob Kiplimo. He ran the same distance in 57 minutes and 20 seconds. The machine beat the peak of human athletic performance by nearly 7 full minutes. This event demonstrated that in the realm of raw, continuous physical output, mechanical endurance can now outpace human biology. You might expect a machine like this to come from a major military contractor or a specialized robotics lab. Instead, Lightning was built back on Honor, a Chinese consumer smartphone manufacturer, which raises a rather obvious question. Why is a cell phone company investing millions to put over 100 bipedal robots on a parallel running track at a public sporting event? The answer lies in a testing vacuum. Modern robotics engineers can design incredible machines in highly controlled laboratories, but a smooth, pristine lab floor completely fails to replicate the chaotic, sustained physical stress of the outside world. Putting these machines on a public course with thousands of moving variables acts as a massive-scale crucible. It forces the autonomous hardware to survive the elements in real time. Only 12 months prior, the inaugural 2025 race was a failure for the machines. The winning robot that year hobbled to the finish line in a sluggish 2 hours and 40 minutes. The rest of the robotic pack fared even worse. The majority of the models were too physically fragile to sustain the impact, breaking down mid-stride and failing to finish the course. To solve that frailty, the engineers started by rethinking the 2026 model's biomechanics. They gave Lightning elongated legs, measuring exactly 90 to 95 centimeters. These dimensions were calculated to replicate the exact stride and gait mechanics of elite human runners. Then they let the robots think for themselves. Instead of relying on a human with a remote control, nearly half the machines used onboard sensor arrays. They self-navigated a parallel track, actively dodging barriers to avoid colliding with human athletes. Taking a machine from a brittle, remote-controlled toy to an autonomous, record-breaking athlete in a single year shows the hyper-accelerated iteration cycle driving applied robotics today. But running fast creates a brutal physics problem. Extreme heat buildup is the single greatest threat to continuous robotic movement. When these heavy metal joints cycle back and forth thousands of times a minute, they generate intense friction. Standard cooling fans simply cannot push enough air to disperse that thermal energy inside a compact housing. This is where Honor's consumer electronics background gave them an edge. They took the advanced liquid cooling systems they developed for high-end smartphones and ported that architecture into the robot's chassis. By pumping fluid through a continuous liquid cooling cycle, they constantly stripped the heat away from the motors. This allowed Lightning to operate at maximum speed for 13.1 miles without melting its own internal components. Lightning's record-shattering victory was ultimately a triumph of thermal management. According to the project's lead engineer, Du Shouty, building a robot simply to run fast is mechanically meaningless for its actual daily utility. The half marathon was a data-gathering exercise disguised as a sporting event. It provided the stress test needed for two specific metrics: the efficiency of the liquid cooling system and the overall structural reliability of the frame. The real destination for this hardware is the automated factory floor. If a robotic joint can survive pounding the pavement at full sprint without fracturing, it possesses the durability to work an assembly line. It can build cars or sort packages, operating tirelessly. The spectacle in Beijing provided the exact telemetry needed to integrate high-speed reliability into industrial production lines. Local spectators watched the machines fly past with a mix of awe and tangible concern. It's a sobering reality for human athletes who spend months punishing their bodies to prepare for a race, suddenly faced with a silver rival that doesn't even have a pulse. Though the hardware still has a few bugs to work out. During the race, one robot tripped flat on its face at the starting line, while another wandered into a barrier. Human athletes can keep their medals. Lightning exists to show that the engineering behind tireless, autonomous physical labor has moved out of the laboratory and onto the pavement.